Good morning. Welcome to this video lecture on field theory. In this video, we will learn the mathematical fundamentals that are essential to learn the concepts of field theory. We will see what is field. If we have a quantity and if the quantity is distributed in the space or spatial distribution of a quantity, we call it as field. The study of such fields, its physical behavior and how the manner it interacts with other matters or other field, we call it as field theory. Like if we study a field around a conductor, we call it as electric field. If we study the magnetic pattern around a magnet, we call it as magnetic field. And whatever the earth, if we study the gravitational field that is existing around the earth, we call it as gravitational field. We'll get into the basics, vector calculus basics. We know what is a scalar. If we describe a physical quantity only by a magnitude, we call it as a scalar quantity. You can have few examples here. Like suppose if I take up the speed of a vehicle, right? If I describe the speed of the vehicle as 20 meters per second, then speed is going to be a scalar quantity, right? Here we mention only the magnitude. We don't bother about the direction. Time is another example for a scalar quantity. The same way, we can have a vector quantity also. When it comes to vector quantity, we describe both the magnitude as well as the direction. The best example is force. Suppose if you mention the force, we can mention the magnitude as well as the direction of force also. The drag force, the lift force, thrust force, all these things comes under vector quantity. We can describe it as a vector quantity. And when it comes to a unit vector, a vector which has got a magnitude of unit length is called a unit vector. And normally we go with a coordinate system of three-dimensional, and in such three-dimensional, a unit vector can be expressed as a vector divided by its magnitude. If you take up the properties of the vector, if we consider three vectors A, B, C, and a scalar M and N, then we can prove the properties of the vector obeying certain laws, right? If we go with the addition of vectors, we can see that the addition of vectors obey commutative law and associative law. If you take up the subtraction, right, it could be it can be done as a addition only. So we take up one vector as a negative vector, right, or a vector with negative magnitude, or a vector with magnitude, positive magnitude with a direction in the opposite side. If you take up the multiplication of like a scalar quantity with a vector quantity, this multiplication property, it abides commutative law, associative law, distributive law also. The multiplication of vectors, the previous case we saw multiplication of a scalar with a vector. Right, if you want to multiply two vectors, then how it can be done? It can be done in two ways, either by going with a dot product or with the cross product. If you take up the dot product, we call it as scalar product of two vectors, and we write it as A dot B. A dot B is equal to magnitude of A into magnitude of B into cos theta, where theta is the angle between the two vectors. Suppose if you take up the angle as 0, automatically it is going to be magnitude of two vectors. So A dot B is equal to just magnitude of A into magnitude of B. And if you take up the dot product of vectors, the properties of these dot products, these dot product obeys commutative law. That is, A dot B is equal to B dot A also. When you take up the scalar product of dot product, right? It obeys both the conditions. Suppose if I multiply, if my A vector has got a scalar quantity also, that is P into A, and another vector Q into B, and if I multiply it automatically, you can have it as P into Q into A into B. Okay. And the dot product of a vector is the magnitude squared of a vector. Okay, right? So suppose if you have two vectors of equal quantity, and if you do a dot product, automatically A into A, it becomes A square. And we can very well see that dot product, it follows distributive law also. Moving on to the next method of multiplying a vector, multiplying two vectors, we can go with cross product. When it comes to cross product, we write it as A cross B. So A cross B is equal to, right, A magnitude of A into magnitude of B into sine theta. We write it as sine theta. In previous case, dot product, it was cos theta. Now here it is a sine theta. So normally we represent this cross product in matrix form. When it comes to matrix form, we represent the axis first, then the vectors and the magnitudes. And if you take up the properties of the cross product of a vector, it has got anti-commutative property. Normally we say it obeys commutative law. Here it is anti, because it is, when I go with A cross B, it will be equal to B cross A, but here it is anti, so automatically it is minus B cross A. Then it obeys distributive law also, and it has got zero vector property. So when I say A cross B is equal to 0, it means that either A vector is 0 or B vector is 0. So these are the properties of a cross product. Suppose if the dot product happens to be 0, it means that these two vectors are perpendicular to each other. If the cross product happens to be 0, it means that these two vectors are parallel to each other. So we can find out whether the vectors are parallel to each other or perpendicular to each other by either taking a dot product or a cross product. Moving to the other math fundamental that is involved here, it is the gradient. Normally, we like gradient of a function is a vector quantity. It is a vector quantity, and we represent gradient value with nebula, right? So we write it as nebula vector or del into vector, right? Any way we can represent it. And suppose if I have a vector like this, right? F is equal to a component of fx and component of fy and component of fz, then automatically del f is equal to dou f by dou x of I vector plus dou f by dou y into j vector plus dou f by dou z into k vector. That is, if you take up the gradient and if it the magnitude shrinks to 0, and the vector when you take up the differentiation, it should lie in the plane. Next, another mathematical fundamental that is needed is divergence of a vector. Normally, to a vector, we are going to take up a dot product. So divergence, we write it as div, right? So again, we are going to represent it with del dot f, right? So dot f is meant for divergence. So when you go with divergence, automatically it gives you a scalar value. And if the divergence value happens to be greater than zero, it means that whatever space that you have, right, it is going to be a sourcing, right? It is going to have a sourcing property. If the divergence is less than zero, whatever whatever quantity that we have considered, it is going to be of a sinking property. And if the divergence happens to be zero, then it becomes incompressible, right? Incompressible. Then we can say the vector to be like suppose if we take up a divergence of a vector, and if the vector happens to have zero value, then we can call it as a solenoidal vector. And we can say it is incompressible. When you say incompressible, it is neither sourcing nor sinking. The next fundamental that is curl of a vector. When you take up a curl, it becomes a cross product. When you take up the when you by like by the name itself, we can say that it is going to have a rotational property. It is going to have a rotational property. And if the curl happens to be zero, then we say that it is a irrotational vector. It is a irrotational vector. If the curl has a value, then it becomes a rotational vector. And the curl can have a positive value as well as a negative value. The orientation, the direction changes. Hope you will be able to take up the small assessment that is given. Thank you.